Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part 3 of Analyzing Hydrologic Time Series. Okay, this is the 4th lecture in the Statistical Methods on Hydrology class. So now we're going to get away from looking at the extremes of our data set and go back to working with all of the data. So working with daily flows, we're no longer able to make the assumption that our data points are independent of each other. The flow today is very closely related to the flow yesterday, and a reservoir stage even more so. So these daily or shorter values are persistent. Right? So we can't simply do a frequency analysis of our data points to estimate probability. First, we're going to talk about duration curves. Now, by unfortunate coincidence, we're again using the word duration. Here it means something different than when we talked about longer duration average flow or volume up here. Duration is not meaning a duration of time in this case. In fact, I can't actually say where the name duration curves came from, but there's something a little bit different. So the duration curve is based on characterizing the entire data set of daily values. So it's based on pooling all of the values in the time series and computing the fraction of days that exceed a particular level, referred to as percent of time exceeded. So this doesn't explicitly estimate probability, although there are times that we use a duration curve because we do need probability estimates. So we can say that the duration curve is an estimate of the likelihood that a daily flow value, right, not an annual extreme like the frequency curves were, but an estimate of the likelihood that a daily flow value will exceed a particular level. We just have to be careful that we are referring to a time in the future, not sometime soon, so when we're separate from the level that flow is at today. Right? The duration curve is a graphical display of stream flow characteristics, which we'll see on the next tab. We use it for navigation and for run-of-river hydropower. We use it for water supply. We use it for any time where we need to know how often flow is at any particular level. Right. So here's the computation. It's really extremely simple. And in fact, like many of the things we've talked about so far, it's just a relative frequency, right? So we're going to take all of the daily flow values for the period of record and rank them from largest to smallest. And then for each, compute the percent of time exceeded by rank over total number of days in the records, right? So if rank is the number of times that you equal or exceed a value, then this is just the relative frequency of equaling or exceeding any value, right? So very simple. So here is the regulated flows on the American River from Folsom Reservoir. This came as the result of our reservoir simulation model. And let's say we're interested in hydropower generation. Right, so maybe I'll ask the question, how much of the time can we expect future flows to be between 2,000 and 4,000 CFS? So maybe that's the range in which we can operate our hydropower turbines. So first, I'm going to change the axis of flow into log scale so we can see that 2,000 to 4,000 range a little bit more clearly. Right? Then I'm going to take all of these flows and pool them together and sort from largest to smallest. And on the horizontal, I'm going to plot the percent of time exceeded with 0 on the left, 0 on the right, and 1 on the left, right, to produce this duration curve. So this shows us how often flow is in each range, right? It's ironic that we've actually lost the duration of time that flows might have been in a particular range because we've pooled them all together. But overall, we know how often flow is in certain ranges. So to answer our question of how often is flow between 2,000 and 4,000 CFS, here's 4,000 CFS, and we have a bit of a flat spot here at 4,000 because we have many days that were at exactly that flow. But if we look at how often flow was larger and not inclusive of 4,000 CFS, it's 19%. Here's 2,000 CFS, and if we want to look at how often flow was equal to or greater than 4,000 CFS, we're going to come to the other side of the flat spot and get 70% of the time. Right, so then, therefore, the amount of time flow is between 2,000 and 4,000 is 70 minus 19%, which is 51% of the time. Right, so half the time flow will be within the range that releases can be used to generate hydropower. right? Just for interest, here is a similar here's a similar duration curve plotted for unregulated flows, just to see what it would be like if this was a run-of-river hydropower plant. So now if we're looking at the amount of time between 2,000 and 4,000 CFS, we're just going to have the range between 30 and 44%, and so only 14% of the time would the turbines be in their optimal range. So in this example, I used all of the data for the entire year. There are times when you might care only about a particular season. If you want to know, perhaps for restoration analysis and habitat, how often flow is within a certain range only during the spring, you could perform the same analysis, but only use flow within a certain season of each year. It would still be all years, but limited to, say, only flows from March 1st to June 30th. Right? Otherwise, the same analysis. Right, some cautions for duration analysis. We have to recall the points aren't independent, and so frequency doesn't approximate probability in the near term. It only approximates probability in the future. And also that the estimates of probability that we might use in the future are daily probabilities and not annual probabilities. Analytical distributions don't tend to fit the data. Also, even though it looks like we have a lot of data points because we have 365 and a quarter values per year, we still need a sufficient record length to be estimating the tails of our distributions. Okay, another type of analysis that we sometimes do with all of our daily flows and stages is something called summary hydrographs. Again, we have to be careful with the name because it's not actually hydrographs that we'll be creating. So here's some data from Rio Madeira in Brazil. And this is a plot like we see from SSP, in which we plot all of our historical record 1 year at a time on top of each other. So this plot goes from January through December, and each year of flow is a different color, just to make it a little bit more visible. But what we do in this case is isolate 1 day of the year at a time. So I'm going to show isolating September 1st. Right, so I'm going to take the September 1st value from every year of my record. Right, here's my histogram of my September 1st values. And the red line is on the right axis, just a cumulative distribution of these values. So from the cumulative, I can say, well, 90% of the time, my value is less than 7750. The median of my values is about 4834. So this gives me a frequency analysis of only September 1st. I can then use those values on September 1st and do the exact same analysis for every other day of the year. Then for each day of the year, I can plot curves that are representative of those percentiles, right? So my 90% value is plotted here in pink separately for every day of the year. My median value is plotted in green for each day. However, it gives us a very interesting depiction of what the hydrology looks like at the site. You know, we see the gradual increase and then decrease of the flows. Didn't mean to advance the slide there. We see the dry time of the year and the wet time of the year. The two extreme lines, the gray dashed lines, are the maximum and minimum of each day. To look at the same type of curves for the American River below Folsom, we've got the unregulated version on the left and the same analysis of regulated flows on the right. So this shows us very clearly for the reservoir inflows, we have the very dry summer with very low flows, and we've got the wetter winter with higher flows. On the regulated flow side, we see that in the summer, the flows aren't quite as low for the releases because we're generating hydropower. Now note, these figures don't contain the maximums, and I'm going to now change the vertical axis and include the maximum flow. Now this watershed experiences rain floods more than snow melt, and so what we see with the maximum flows is that each day of the year might have experienced a flood event in the historical record, and so we're seeing all of those flood peaks, you know, each on their different days. Okay. we see the flood season based on the maximums much more clearly than we see it based even on the 90th percentile. So another example is the Columbia River at the Dalles. This is a snowmelt watershed, which I don't want to say instead of a rain flood, but primarily snowmelt. So again, we have the unregulated flows on the left, the regulated flows on the right. This watershed has a series of reservoirs to decrease the snowmelt peaks by storing a lot of that water in each of the reservoirs during the season. So in this watershed, the summer values are not all of that much different. It's mainly about operating for the flood peaks. And we have a threshold level at 600,000 CFS, which is a target for keeping flow at the Dalles below. So if I change the axes again and put in the maximums, we see that primarily the snowmelt peak is what is of interest and what's being decreased, but there's also some rain floods in here during the winter season. And if we look over on the regulated side, we see that for almost all of the simulated record, it was possible with operation of those reservoirs to keep flow below the threshold. Okay, so that is the end of video number 3, and we will next move on to video number 4. I will see you there.